So far I have discussed why analog electronics is important. So I've shown you that what are the different typical components of an analog electronics device, for example, the filters, amplifiers, ADCs, etc. Then I have shown you a few of the examples like how in digital communication analog circuits are important, because at the output side you get something which is distorted, so you need help of analog circuits to retrieve the data. There are also examples like binary and multi-level data where analog circuits are required. Another example was like storage disk drive, that is the hard disk or hard storage memories that we use, wherein we need to recover data from this kind of retrieve data after storing. So in that case also we need analog circuits. Just a quick recap of the things that we have done. Then in wireless communication we need, because we have interferers like this, so either we need to push them away from the desired frequency, or we need to boost this desired signal to a higher extent so that these interferers become less in magnitude. Apart from this, we also have shown the optical receiver system. In optical receiver system, at the receiving end you need analog circuit, because you are processing an analog optical signal, so you need analog circuit for that purpose. Then in sensor system I have shown you two examples of accelerometer. One is simple accelerometer, another one is differential accelerometer, wherein the capacitance was taken as the parameter, and I have shown you that capacitance is a function of distance. So if the distance reduces, the capacitance will be higher. Actually capacitance is epsilon A by D. This is the relation between capacitance and distance. So if D is less, C will be higher. That's why based on the deflection you'll get to know what is the acceleration. As the system is accelerating, this will start deflecting. So from that deflection you can calibrate the acceleration, and then you can use this sensor for different purposes. Okay. Then different biomedical application also I have discussed, like controlling blood clotting, different ECG, EMG signals, biosensors, robotics and implant surgeries, point of care device, signal conditioning and sensor interfacing. Then a simple impedance measurement circuit was discussed, wherein different analog components are there along with some of the digital, and then a simple sensor system, just to give you an idea how it is used. Now today we will discuss the purpose of analog circuit, why we use analog circuit. So it is written, all kind of sensors such as optical, mechanical, thermal, magnetic provides analog voltage signal as output which is susceptible to noise, which I already have said. Any analog signal is susceptible to noise, because when you have an analog signal like this, say it's a sinusoidal signal, and if there is some variation in the input signal, and if you are using an amplifier, the same variation can get amplified in your output, so which is not desirable. So this is, for that purpose you need filters, you need low noise amplifiers. So these are analog circuits. So in such a case, low noise amplification, filters, ADCs are required, as I have said. So long distance transmission of digital data suffer from distortion, hence analog like transceivers are required. So I already have shown you one example of optical fiber, wherein the output signal is not same as the input one. In fact, it is highly distorted. So you need an analog circuit to retrieve that data back from this output signal. Then data in many storage devices like HDD is weak in nature. So I have shown you that the noise level can go up to as high as 2 millivolt. So in that case, recovery of the data from the hard disk is required, and this is done by analog circuits. So in this case also you need analog circuit. Similarly, signals received by antenna in wireless communication are usually very weak. So that also in an example I have showed, that sometimes you get interferers which is even higher in amplitude. So in that case, you need analog circuit either to shift them apart from the main required frequency, or you boost up the original frequency. That is also done by an analog circuit. So these are the purpose of analog circuits, remember. Then high speed microprocessors and memories use clock signals. Now this is an interesting thing. In memories and microprocessor you need high speed, okay, and for that purpose you use clock signals. Now there is a problem in clock signals sometimes that digital guys found is, say you have a clock like this which you are expecting to appear at t equal to t0, but due to some reason means the interconnects, especially because of interconnects, because inside a chip you have long interconnects. So even if the chip is very small like this, you'll find there is lot of interconnects like this. So the interconnects lengths may go in kilometers, in fact. So that signal is traveling a long distance. So it may happen other than t equal to t0, the signal is appearing at t equal to t0 plus delta t. Now this creates a problem. Now this is a digital electronics problem, but to get rid of this problem you use PLL, phased lock loops, which is again an analog circuit. So for this purpose also we need analog circuits. Then, as I have said, there is no ideal interconnects exist in the packaged devices. So large number of interconnects leads to transmission line effects while signal is flowing, which is also where also we need analog circuit to get rid of this. Sense amplifiers are used in memories and are essential, and which are essentially an analog device. So sense amplifiers are like, sometimes what happens, you need 1 volt. Now it may happen that this particular amplifier will enhance the voltage that is receiving by certain margin. So if the signal is reached up to 0.6, this amplifier will amplify it till 1 just to make the performance better. So this type of sense amplifiers are also analog circuits. So this is basically a comparator kind of thing. It will compare that whether the signal is reaching 0.6 or not. Once it is reached 0.6, it will increase it up to 1 to improve, and this improves the performance. There are different challenges also in analog circuits. As I have said, one of the major challenges is multi-dimensional trade-off. In digital circuit, the trade-offs are mostly between speed and power. But in analog circuits, there are multi-dimensional trade-offs like speed, power gain, precision, supply, bandwidth. So precision means if you need, say, 1 millivolt, it has to be 1 millivolt. You cannot afford 1.1 millivolt even, because a 0.1 millivolt may get amplified in the output by a factor of 20, 50, 100 depending on the amplifier you are using. So it has to be very precise. Then analog circuits are more sensitive to noise, crosstalk, and multiple other interference. So noise, I already have said, they are more sensitive to noise. And why they are more sensitive to noise compared to digital? Because when you use digital circuit, so you define a threshold, right? You define a threshold. Now above this threshold it is 1, below this threshold it is 0. So even if there is some ripple, some noise in the circuit or in the signal, if it is above threshold, that noise doesn't matter, because ultimately you are getting 1. So you have not to be very much precise about the signal that you are getting above this. So in that case, digital circuits are good. They provide very good noise margin. But in case of analog, as I have said, a 0.1 millivolt may get amplified somewhere else. So it is more susceptible towards noise. Then analog circuits are sensitive to second order device effects. Now this I will tell you why I have said this. Second order device effects means It may also start, say if you have AX, your signal is AX plus A1x square plus A2x cube, something like this. So these device effects may come. One of the purpose of using the analog circuit is to suppress these things. If you don't suppress these things, because it's a linear circuit, analog circuits are linear circuits, so you will only use the linear term while you are operating this circuit. But these type of interference may appear, which you need to suppress. I'll discuss it in detail maybe in the few slides or even in later lectures. Now automation is a challenge. As I've said, it's customized, right? For each system you need to design your analog circuit again from the beginning. It's not like digital that you have multiplexer, adder, these things already in your bucket. When you need a larger circuit, you just bring it in, connect it and make a larger circuit, which is possible in digital, but in analog it is not possible. It's completely customized. And modeling and simulations are also not very straightforward. Many things you will do based on intuition, so you need experience. Okay, then integration of analog and digital function into a same substrate. As I've said that everyone is using CMOS in digital, so you are bound to use CMOS in analog as well. So this is another challenge. Even CMOS is not the best possible device. You have to design with that just to make it compatible with, make it compatible with digital circuit, and you can use both in the same single chip. Now this is the analog and digital design difference. So analog design is comparatively complicated. As I've said, it's customized, so it is little bit complicated. In case of digital design, noise margin is large. So as I've said, already shown that if there is a threshold, even if there is ripples, and if it is not crossing the threshold, that is fine. But for analog, this is not the case. In analog, it's a small ripple may create a very big problem. Then trade-offs are less, only between power, speed and area. But in analog, it's a multi-dimensional trade-off, as I've said. Now analog circuits are sensitive to noise and crosstalks. Now crosstalks, what is crosstalk? Crosstalk means if you have two lines, this is say parallelly they are carrying signals, then the signal in this may interfere the signal in the other line, and signal in this may interfere the signal in the other line. This is called crosstalk. Both the lines are carrying the signal, but one signal is influencing the other, which is not desirable. So there are crosstalks in analog circuits, which is more significant. Now second order device parameters of device effect, which affects the analog circuit. Second order device parameters also affects the analog circuits. As I have said, AX plus A1x square, A2x cube. So in that case, the second order thing will affect the device parameters. Now automation are difficult. That I also already said in the previous slide, that automation is not very straightforward. Now the technologies. There are two technologies that we use readily for analog circuit. One is the bipolar junction transistor, another one is the FETs, field effect transistors. Now BJTs are better than MOS in terms of performance, that is speed and gain, but suffers from high power dissipation. Now power is also a problem. Even BJTs are good, but they use, the power dissipation in these devices are very high, and which is not desirable, because ultimately power is an issue. You don't want to lose a lot of power in your devices, then your battery will drain faster. So even if the performance is better than MOS, ultimately you will lose power. And I will show you how you are going to lose the powers, because gain, etc. is a function of the biasing current. Now if you increase the biasing current, your gain will be better, or maybe your bandwidth will become better, but you are losing power, so it is not ultimately desirable. Then MOS, though not the best option for analog, is preferred for digital circuits because it has low power dissipation and high density of device. You can make small devices compared to BJTs. Scaling down BJT is not easy. It's to some extent is not possible. But in MOS, we are now working in 3 nanometer channels. I mean, recently in some research in Korea have shown 3 nanometer multi-gate technology. So you are actually reducing the size of the device, which enables large scale integration. So CMOS is the best available technology for digital circuits, and hence analog circuits are also supposed to get implemented in the CMOS that I already have mentioned. Now that is why the mixed signal analysis concept came. You need analog and digital both together. This is called mixed signal analysis, and that's why I've shown you a simple example that you have a sensors, there is some analog part, there is some digital part, but they are both has to be in the same substrate, both has to be in the same place. Now this is an simple example of digital versus analog. Now if you see the digital circuit, you will find that this is completely non-linear. These are not linear circuits. Why it is non-linear and why we call this as linear? Now even if you find the circuit, you will see there is an MOS, right? FET device is there, but the characteristics is not linear. FET characteristics is not linear. It's something like that, right? It's non-linear characteristics, output characteristics. But why then we call it linear and why it is non-linear? Now if you see this circuit, the digital circuit, there are two transistors, right? Two devices. Now in that case, if one is in saturation, maybe other one is in active region. One is in active, the other one is saturation. Both probably may be in the saturation. In such a case, the characteristics of this kind of device becomes highly non-linear. Okay, however, in case of analog, we only operate the whole circuit in the linear domain. Linear means mathematically it's like y equal to mx plus c, something like that. Your characteristics, wherever the characteristics is linear, will operate in that domain only. That's why in analog we have a restriction of input voltage. Wherever in digital you can take advantage of the entire range. Now for example, if this is the transfer characteristics of CMOS inverter, the transfer characteristics of CMOS inverter. So you will see digital can go from the entire range they will use. However, for analog people, they will only look for this linear part. Okay, they will not go beyond the linear part. And why they will not go beyond? If they go beyond the linear part, the other interference may come up. This A1x square, A2x cube, something like that. These interference will come, and once these interference comes and they become dominant, you are going to lose powers for nothing. So we don't want that to come. So it might be little steeper like this, but for the sake of understanding, I made it little wider. Now you have to operate your device operate your circuit in the linear domain. Now it depends on the biasing. Say if you bias your circuit in this point, then you use your input which always stays in the linear domain. So you have a very small signal, you have a restriction. You can't go beyond this. You can go beyond this, then you need to suppress the other part of the signal, or it may create problem. So there is a restriction. So it also depends on your biasing. So biasing also is important. If you can't bias your circuit properly, your device properly, if it shifts somewhere here, then one portion, say if it is shifting in here and you are using this, then one portion of your signal may go in the nonlinear domain, which will create a problem later. Okay. However, for digital, you can use the entire signal. Okay. Now this is a comparison table. So the linearity for analog, it is highly linear. As I have said, it's highly non-linear. Noise immunity is high in case of digital. I already have said the reason why it is high. Whereas for analog, it is low. Power supply variation. For power supply variation, analog circuit is sensitive. I already have shown. Power supply means the biasing, right? It depends on your biasing, depends on the power supply. So if your power supply is, say, is not very properly given, or if it is changing, then there will be a problem in the analog circuit. Now information for analog circuit, they carries n bits of information. For digital, it's just 0 and 1. For analog, it's a lot of information. This is one advantage also. Okay. Now the consideration of analog circuits. Analog circuit is dual rail. That means it can go both positive and negative, plus VDD, minus VDD. Whereas in case of digital, it's 0 to 1. So it probably not goes to the other side. Biasing. Biasing is a very important consideration. I already have said, if you change the biasing, it may happen that your one portion of signal is entering into the nonlinear domain. So biasing is important. Linearity is important. If it is nonlinear, entering into the nonlinear domain, you will be in trouble, because the other interference will come, the higher order interference. Noise tolerance. So you have to take care of the noise tolerance things. They are not immune to the noise, the analog circuits. Low drift. Low drift means your power supply should not drift from one value to the other. You have probably biased it in 5 volts, suddenly it became, say, 4.2. It's not a good thing. So you have to consider a low drift. Then low voltage and low power circuit, which is always desirable. You want low power, you want low voltage. But in analog case, it's not very easy to realize. So, however, the target is you have to use low voltage and low power. Okay. And there are few key parameters for the design. One of the most important parameter is transconductance, GM. We will discuss all these things in the coming classes. I am just introducing all the terms, all the different aspects of the analog circuit. So transconductance is one of the very important parameter. Which is, what is transconductance? Which is output current by input voltage. Right? So transconductance is a very important parameter that we have to consider. Then there is output resistance, which is also important. Now output resistance ideally should be infinite. However, you may need to change the output resistance for different applications. But whether we can change the output resistance or not, this is a question. So in coming class, I will be deriving equations for output resistance, GM, then you will get to know how they are influencing the circuit. So currently I am just introducing the terms. So there is another thing called input referred noise. And the other thing is frequency response, that is bandwidth. Bandwidth is again very important. So after transconductance, bandwidth is very important. You want to use your circuit for a larger bandwidth. So again, it doesn't mean that I'll go on very large bandwidth, because if you try to increase your bandwidth, you may compromise something else. So it's a multi-dimensional trade-off. You have to satisfy everything while you are designing the circuit. So this is one of the major challenge in analog circuit design. However, we will see that what are the things that will influence the entire circuit analysis. So these are the major parameters for analog circuits.